Hello everyone, I am Mondal from Department of Chemical Engineering, Sapienza University of Rome. Welcome to 26th International Conference on Fracture and Structural Integrity. On behalf of my supervisors, Professor Daniela Pilone, Andrea Brotzu, and Ferdinando Felli, this is my presentation on the effect of heat treatment on mechanical properties of FeMnAlC alloys. So the research in these alloys started in 1880s, but it was 1980s when these were seriously considered for a substitute for conventional stainless steel, since manganese and aluminium were very less expensive than nickel and chromium counterparts. Research was carried out on different aspects of these alloys such as mechanical properties, oxidation resistance, corrosion, welding, etc. Based on research, it was found that it had an exceptional combination of mechanical properties such as low specific weight, exceptional fatigue properties, high strength and toughness at room temperature and low temperature, good oxidation resistance at elevated temperature, and ability to age harden and absorb energy on impact. In the present day, this alloy finds its application mainly in cryogenic applications and aircraft and chemical industries with specific composition recommended for each kind of application. Presently, it has again become a hot topic of research for lightweight, crash-resistant car body structure because of its lightweight and ability to absorb impact energy. Now, the alloys in consideration are two types of alloys which were named B23 and B37. It can be noticed that in B23 the amount of aluminium and manganese are higher, which is 39% and 6.5% respectively, whereas in B37 the aluminium content is 4% while manganese is 36%. Now coming to the procedures can be divided into two halves. In the first half, the steel was tested without any kind of thermal treatment, while in the second half, it was tested after being solubilized at 900 degrees Celsius and age hardened for 16 hours at 550 degrees Celsius. The steps for this experimentation can be divided into grinding, polishing, followed by etching by needle solution for 75 seconds, then optical microscope and some analysis, followed by hardness test before and after heat treatment. Then a tensile test before and after heat treatment was done. This was followed by a fracture surface analysis of the broken specimen, and finally an XRD analysis on B23 before and after heat treatment was done. After grinding, polishing, and etching, both the alloys were analyzed for their microstructure without heat treatment. Here, as you can see that both the alloys have similar kind of microstructure, that is austenitic in structure, and both of them have visible twins. A hardness test and density measurement was carried out on both the alloys before the process of heat treatment. For this, a Vickers hardness test was done. As you can see that the average hardness for B23 is 208.6 and the average hardness for B37 is 175.5. Later, a density measurement was carried out where the density of B23 was 6.47 grams per cubic centimeters and the density of B37 was 7.08 grams per cubic centimeter. Since this kind of alloys are known for their good aging properties, both the alloys were subjected to an aging test at 550 degrees Celsius after being solubilized at 900 degrees Celsius. These two graphs shows the Vickers hardness test at different aging durations. While the hardness of B37 is more or less constant after a few hours of aging, it is B23 that becomes interesting, as it can be seen from the graph of B23 that there is a sharp and substantial increase in its hardness with respect to aging duration. In order to study the change in mechanical properties, both the alloys were subject to tensile test before and after heat treatment. This slide shows the tensile test results before heat treatment. It can be seen that for B23 the yield strength is 450 MPa with ultimate strength and elongation being 726.4 MPa and 21% respectively. While for B37 the yield strength is 402 MPa with ultimate strength and elongation being 800 MPa and 30% respectively. But after a heat treatment of 8 hours, things become more interesting. When we carried out tensile test on both the alloys after 8 hours of heat treatment, the nature of B37 did not change, while the nature of B23 changed completely. After the heat treatment, the yield strength of B37 was 422 megapascal, while the ultimate strength and elongation were 817 megapascal and 38% respectively. But when B23 was subjected to heat treatment, the alloy became very brittle and broke with very little load without going into the plastic region. In order to study this change in behavior after heat treatment, the microstructure of both the alloys were again analyzed. While B37 has the austenitic structure as before with visible twins, it is B23 that has completely changed its microstructure. From the picture in the center, it can be noticed that B23 has also formed delamination layers after heat treatment. To study this brittle behavior of B23, it was subjected to X-ray diffraction before and after heat treatment. Before heat treatment, it can be seen that B23 has only austenitic phase with a little amount of ferritic phase. While after heat treatment, we can see that it has developed intermetallic phases such as aluminium manganese and iron manganese, which explains its change in microstructure and its brittleness. Coming to the fracture surface following the tensile test, before heat treatment, it can be seen that both the alloys B23 and B37 show similar kind of ductile fracture. There is also the presence of delamination layers that highlight the presence of defects during the rolling process of the material. Coming to the fracture surface following the tensile test after heat treatment, it can be seen that while B37 has a similar kind of ductile fracture like before, B23 shows a very brittle fracture. This is because of the fact that after heat treatment it developed intermetallic phases which were more brittle in nature. Also, after heat treatment, B23 developed secondary cracks in the alloy that assist the fracture mechanism. So, in order to conclude, we can say that the composition affects the behavior of these alloys, especially when the alloy works at a temperature above 500 or 600 degrees Celsius. The alloy with higher quantity of manganese and aluminium become brittle due to the formation of intermetallic phases. Lastly, it is of paramount importance to optimize the chemical composition of the alloy in order to guarantee a high fracture toughness at high temperature. With this, I finish my presentation. Thank you.